The comparison operators allows us to create Boolean tensors by comparing tensors values element-wise. This operator, it's right over here when we compare the NumPy data inside the tensor with the minimum value. We can do the same if we overload the comparison operators. Let's start from less than, and we have self and other as the data type. We return back the tensor. Okay, and first action, all the time when we work with the other data type, we need to run tensor dot datagate and put other inside the datagate. And we return back the tensor with the self.data less than the other.data. And we return back the tensor with the Boolean data that we can use for our comparison methods. Okay, and then let's define next greater than. So it's all the time pretty similar method body, but in this case we need to run greater than the other data. So it's pretty similar methods, yeah, but with different comparison operators inside. Okay, now we can create the tensor B. And let's say with 4, 2, 3 and 5. We can compare A less than B. Okay, and of course we need to recreate the tensor, and you can see the result. Yeah, we just compare each element of the tensor. Yeah, we can run different operators like equals or not equals. Yeah, everything works fine. The next piece is the static method. Let's define where, and where requires 3 arguments: condition as the tensor, we have tensor A and tensor B, and where returns back the tensor, and where performs element-wise selection based on a condition. The function returns element from the tensor A if the condition is true, and the element from the tensor B if the condition is false. Yeah, so we take element wise from A or from B based on the element from the condition. Okay, and we can make output as the first step, and we run just NumPy where we have the condition data, we have A data and B data. Just because we have tensor A and tensor B requires gradient, we compute the requires gradient based on A requires gradient or B requires gradient. If one of the items requires gradient, we just need to add the dependencies to the gradient computations. Okay, good. And then if A requires gradient, let's think for a moment. We take pieces of information from the tensor A if the condition data is true at the exact indices of the condition data. It means then when we goes backward, we contribute, we commit to the computational graph only items from the tensor A when this condition is true. Otherwise, we just return 0. So we need to define the backward method, like backward A, and we return the numpy where the condition dot data. When this condition data works fine, we need to return the gradient because it's just first place array. Otherwise, we return 0. It means that we return only pieces of the gradient for the backward A that contributed from the tensor A. And we need to define dependencies list. And let's add append to the dependencies leaf. Of course, we are working with the node with the tensor A, value A, and the gradient function underscore backward A. And we need to do something similar for the B. And if B requires gradient, we need to check the same condition, but we contribute 0 if the condition is true. Let's contribute as the float data type, yeah. And we have gradient, yeah, in place where it's false, because we need to take only the pieces of the gradient when the B data is activated, when we contributed data from the B tensor. And to the dependencies, we need to append value B, and here is gradient B, of course, and gradient function gradient B. We return back the tensor with the output requires gradient and dependencies list. Let's test this method. We can run the tensor class to recreate the class with all of the methods, and then let's create the tensor C. Let's say that the tensor C just contains only ones. Okay, and we run tensor dot where for the tensor C, for let's say for the A not equals to B, and we return the tensor C in case if it's true. And let's say that we have one more tensor D with full set of zeros, just for simplicity. We return tensor D when this condition is false. So when you can see that we return back approximately similar result. Let's check for the condition more. We have no such items in the tensor A that more than the items from the tensor B, and we return full set of 0. In quite opposite, yeah, when A strictly less than B, we return only 2 items. So it looks like our where with conditions works fine. With the static method where, we can implement several useful tensor operations like minimum and maximum. Let's define static method minimum, define, or let's say maximum. Let's start from the maximum. We have A as the data, B as the data type, and we will return back tensor data type. Okay, first we need to check that the A and B is ready to use, and we can use tensor.dataGate A and tensor.dataGate B. Okay, so let's return tensor.where and compare A and B. In case if this condition works fine, we need to return A, otherwise B. The maximum method applies element-wise maximum operation, and it returns a tensor with the result of this element-wise maximum. And we can make the method minimum. Okay, with the same type signature, we need to run datagate A and B, but we need to replace right over here the condition to the minimum, and we apply the same element-wise minimum operation. These implementations are clean and use where for efficient element-wise comparison. We can push this further and implement, for example, the threshold method that sets values above a given threshold while leaving others unchanged. Okay, we need to define method threshold. Okay, and we have self as the first argument. Then we have the value, or let's say threshold, as let's say float data type, and value as the float. And we need to return back the tensor data type. Okay, and we return tensor dot where, and we have self more than the threshold. In this case, we need to, if it's true, we need to return the self. Otherwise, we need to return tensor value. Okay, if this true, we just return self. Otherwise, we return this value. Yeah, so it means that we just cut values that less than or equals this threshold. We cut them to this value. Let's do one more. Masked fill, and we have self as the first argument, mask as the tensor data type, we have value as the float. Okay, we return back just the tensor data type. Okay, and we return tensor dot where this mask is true, we need to fill to the tensor value. Otherwise, we install self. The masked fill method replaces values based on a Boolean mask. For item that true, we install this value. Otherwise, we leave this value unchanged. We just use self. Okay, and we define sign method, self as the first argument, and I think that this is it. Yeah, we don't need any other arguments. We return tensor back, and here we need to use the tensor where, and where the self more than 0, we need to return 1, and we wrap this 1 as the tensor, yeah, because where it uses the tensor in the conditions, yeah. So, and then we need to reuse tensor one more time, tensor where the self more than 0, every item that more than 0 just falls into this first step. We return 1 in case if it's more, if it's positive value. And where self less than 0, it means that this is the negative value, and we need to return tensor -1. Otherwise, we have 0. So when we, in this way, we cover all the scenarios. Yeah, in case if it's positive, we return 1. In case if it's negative, -1, and 0, we return 0. We can also rewrite the clip method using where. Let's find the clip. Okay, cut the clip method and put it right over here. Okay, we just leave unchanged this type signature, but let's rewrite the body of the method. We need to return tensor dot where, and let's think for a moment what we need to do. If self less than our minimum value, we need to return tensor mean value. In case if it falls into the mean value range, we just return the mean value. So we need to run tensor.where again, and we know that we can use self more than the maximum value. In this case, we need to cut the values to this maximum value, and we need to return tensor max value. We just wrap by the tensor data type this max value, and last step, we just return self. Self, it means that we falls into this range, because for the minimum value we return the minimum value. For the values that more than maximum value, we return maximum value, and otherwise we just leave everything unchanged. I hope that this clip works by the same way as the previous implementation.